All right, this is part two of my rotational inertia lecture where we're going to work some examples. So here we go. Um, we're going to find, I copied this out of someone else's notes. So they call it moment of inertia properly. What does AP call it? They will say rotational inertia. And we have a whole bunch of objects. So here we go. We're going to determine the rotational inertia of each of these objects. So I have an object that has two masses at the very end of something that I'll consider a light string. And I'm going to calculate it as if there's 2 point masses. So this is object one and this is object two. So I of this object will be equal to I1 plus I2. The rotational inertia of a point mass is mr squared plus mr squared. Both masses and r's are the same, so essentially I can calculate 2 kilograms times r is equal to 0.3 meters, 0.3 meters, and square it. And I have two of them, so I've multiplied by 2. And that will give me a value of 0.36 kilograms meters squared. Next, this is a solid sphere. Once again, you will not be required to memorize these, but we can look this up. So we have a solid sphere, and the equation for the rotational inertia of the solid sphere is 2/5 times mass times the radius squared. We know the radius is 0.4 meters. We have a mass of 2 kilograms. So the I value is 2/5 times the mass times the radius of zero point 0.4 meters squared. The rotational inertia of this particular sphere will be 0.28 kilograms meters squared. We have an object they called a log, which is a solid cylinder. And so the equation for a solid cylinder is equal to 1/2 mass times radius squared when rotated about an axis of rotation through the center. And so the rotational inertia of this object is equal to 1/2 times the mass, which is 50 kilograms, times the radius, which is 0.2 meters. So 0.2 meters, and I need to square it. And if I plug that into my calculator correctly, I will get 1 kilogram meters squared. Then this one is not on my examples, but there exists such a thing. That's why we have engineering handbooks. This is going to be rotated as if I have a rod that runs through the center, and this disc is spinning about that axis as opposed to an axis of rotation that runs through the center. So in this case, the I value or the equation for this this is considered a hoop about axis of rotation shown. You would have to look this up. Is equal to actually 1/2 mr squared, which is similar to a solid disk, but this is a hoop, but it's rotating about a different axis. So it is equal to 1/2 the mass, which is 4 kilograms, times 0.5 meters squared, r equals 0.5 meters, and I will get 0.5 kilogram meters squared. This is a rod rotated about the end, and so the rotational inertia for a rod that's rotated about the end as shown is 1/3 as opposed to 1/12, which is rotated about the center, is times its mass times the length of the rod squared. The length of the rod is 0.8 meters. The mass is given in proper units, so 1/3 times 6 kilograms times the length of 0.8 meters squared. That will give me a value of 0.28 kilograms meters squared. Now, let's get into this. The whole profession of engineering lots of times we make educated decisions and guesses or estimates, not guesses, actually. That's very much the wrong word. We will estimate certain things and we have to. And we might have some amount of contingency that we put on this while we're doing engineering calcs. But I'll show you an example of what I mean by that. This is a picture of a sledgehammer, and it's going to get rotated about this axis of rotation. And this is the handle of the sledgehammer, and we're going to assume it's solid. And so that mimics a rod about the end, So we'll call that I1. And then we got the sledgehammer's mallet at the very end, and we're going to assume this is a point mass. And so I'm going to call that object or I2. Okay, so the in rotational inertia of this sledgehammer can be estimated as the rotational inertia of the first piece, which I'm going to say is a rod, plus the rotational inertia of the mallet, which I'm going to assume is a point mass. And then I will use my equations and plug that in. So a rod rotated at that end is 1/3. So 1/3, kind of like what we did before. There it is, 1/3 mass times the length squared. 1/3 times the mass times the length squared. The length is 0.3 meters. I'm going to square it. And now I have a point mass at the end that has, and again, what's a point mass? That's mr squared. So that's 5 kilograms times how far away from the axis of rotation is that? We have to assume that's 3 meters. And we will square it, and we will find that value to equal 1.28. We estimated it to be 1.28 kilograms meters squared. We do that a lot in engineering. Okay. Is that the last one? Yeah, one more. Okay, I have a wheel and an axle. This drawing doesn't show enough, but I borrowed this. These are solid at the ends based on his answers. Let's see if we can get this right. This is a solid piece, and this is a solid piece of pipe. So this has an I value, and notice the axis of rotation is through the center, and that I value is like a disk. This is an I value of a disk. These disks are identical. They have the same radius of 0.5 meters. They have the same mass. So the I value of this object is equal to twice the I value of those disks, plus this right here is a solid cylinder, which is also um, the same as a disk. If you go look at it, but I'll write it as a solid cylinder. And we can calculate it now that we have kind of an estimate of what we're doing. So a disk is 1/2 the mass, so we have 2 kilograms times the radius squared, 0.5 meters, and I'm going to square that. I didn't actually need that. And then don't forget I have to double it because I have 2 of them, so that's why I have a 2 out there. And then the solid cylinder happens to be 1/2 the mass, which is 1 kilogram, times its radius, which is 0.1 meter squared. And if you plug that into your calculator and add it up, we get 0.505 kilogram meters squared. Okay, now let me go to that picture and explain why. There it is. So a solid cylinder, if we just look at a little piece of it at the top, it's a disk. Okay, so the disk and the solid cylinder equations are the same. Okay, all right, that concludes my lecture. Come see me if you have any questions.